going to start by talking about Unit 4A, which is our first foray into energy. Foray into energy. So I call it Energy 1. And energy is kind of a tricky thing to wrap your head around. The reason why energy is tricky is because it is not a real, tangible thing that you can put your fingers on in physics. Whereas with motion, you kind of know what it feels like to walk to class or to ride your bike or to drive in your car, to go somewhere. That's objects moving through physical space that you can see. Or with forces, those are a push or a pull that you can actually feel. There's no way to put your finger on energy. It's a new lens at looking at physics problems. And so it'll take a little bit of time for you to wrap your head around this, but we have 2 weeks to cover all this content. A lot of what we cover today might feel a little uncomfortable at first, but I think once you start seeing it, it will become more clear to you why energy is useful. It's a very clean mathematical way to look at physical scenarios, and eventually you'll start seeing it everywhere. We're going to start by talking about this concept of work. The formal definition for work is a transformation of energy. So it might seem like a little bit of a circular definition to define work by talking about energy, because we don't quite know what energy is, but like I said, once you start seeing it, you'll start seeing it in a lot of different places. And the way that we define work is by talking about a force that acts over a distance, F times d. And you might recall from the PowerPoint that there is a small little tagline that we got to include here, which is a cosine theta. This is our official definition for work. And one example where you might do work is when you are weightlifting in the gym. Maybe not all of us like to weightlift, but this is a great example for thinking about it. So if I'm laying down to do a bench press, that means that I will have a barbell in my hand. I'll have a barbell in my hand that I have to lift, so here is the weight. And you know that when you're lifting anything, you're fighting against gravity. So there's a force of gravity that acts down on this barbell, and that force is dependent on its mass times the gravitational constant of Earth. I'm not going to put the minus sign just so that we can practice thinking about a number that doesn't have the vector arrow above it. So this is just saying the strength of the force of gravity is the mass times the gravitational constant. It does point down. For now, let's just think about it as a number. Every time that I lift up this barbell, I have to exert a force, and that force must be exactly equal to the force of gravity. So I would have to apply a force in the upward direction that is m times g. That's how much I have to do. When I'm putting in work, I apply a force. And I might apply that force over a distance that is a vertical distance upward, d. Now this piece, theta, is talking about the angle between the force that's applied and the distance over which it's applied. So in this case, the force is up, the distance is up, they're in the same direction, the angle between those two is 0. So I would say theta equals 0 degrees in this case of me bench pressing a barbell. If we try to put some numbers to this, we can do some calculations to figure out how much work was done when lifting up the barbell. So let's see, how much can Dr. Weller lift? All right, I'm more of a runner. We'll say that the mass of the barbell that I'm going to lift is 40 kilograms, just a warm-up set, don't judge. And we have, let's say we lift it 0.5 meters. It's about how much you might lift it off of your chest. And so we can do a calculation of the work by saying work equals force times distance times cosine theta. And in this case, the force that I'm talking about is the applied force. So I can plug in mg for that. We'll leave d as the distance and cos theta. And now let's actually put some numbers in and see what we get. Let's say that I'm lifting 40 kilograms against gravity, which is 9.8. We could write it as meters per second squared, or we could write it as newtons per kilogram. I'm going to stick with newtons per kilogram because we're talking about forces. And the distance that I lifted is 0.5 meters times the cosine of 0 degrees, because that is the angle between the force and the distance. We can run the numbers and do a calculation. 40 times 9.8 times 0.5 times the cosine of 0. And I get a number that says my work that I did as I lifted this barbell was 196. Now let's think about the units that come along with that. I had kilograms here and kilograms on bottom there, so those will cancel, leaving me with just newtons times meters. N times M. And this newton times a meter is a very special unit that we call a joule. So, joule is the unit of work and also of energy. Energy and work both have the same units. It's a joule. We use a capital J to denote that, and we could say that 1J equals 1 Newton times a meter. Because distance, that's the equation that we use to calculate our work. So, sort of like when we talked about newtons for force having some units hidden away inside of them, a joule also has units hidden away inside of them. It's composed of more fundamental units than just a newton and a meter. Remember that a newton, we figured out by doing mass times acceleration. F equals ma. So really, inside of a newton, there's also some other units too. 1 joule, we would also say, is equal to 1, and then inside of a newton we had mass times acceleration, so that means that we have to have a kilogram times a meter per second squared, that's mass, that's acceleration, and we can't forget to tag along the meter that we previously had there. So really 1 joule is also equal to 1 kilogram times a meter squared per second squared. Any of these units are actually saying the same thing. 1 joule equals 1 newton times a meter equals 1 kilogram times a meter squared per second squared. Those are all the same units. They are equivalent. You're going to gain some practice thinking about the units when we do our lab today. But what we're talking about right here is called dimensional analysis. Perhaps you've heard that word in chemistry class or something like that. It's basically figuring out what units actually comprise some physical variable. So we've talked about work and the units that go into work, but we haven't talked about energy yet. And work and energy are two sides of the same coin. They're effectively the same thing, but let's be very formal with it and talk about the definition of energy. Energy is the capacity to do work. Like I said, it's a little bit circular. Work is a transformation of energy, and energy is the ability to do work. It's not actually a physical thing. There's no way you can grab onto energy and hold on to it. There's no way you can grab onto work, but it's a very useful way of looking at physics problems. And there are many different forms of energy. We're going to talk about 2 for this week, and then we'll add a few more on next week. The first one that I want to talk about is the kind of energy that we gave to that barbell when we did work. It was called gravitational energy. Gravitational energy is the energy associated with a gravitational field. So we are all living in a gravitational field right now on Earth, and the way that we give an object gravitational energy is by lifting it up. We do a force over a distance. So instead of a barbell, here I have a brick, and if I lift it, that requires me to use a force, and I exerted it over some distance, and so this brick right now has gravitational energy, and I did work to give it that gravitational energy. The official equation for our gravitational energy is Eg, we use a little subscript g for gravity, equals mgh. We need to include a little note about this h. Here, m is our mass, g is the gravitational constant. You're used to seeing that one by now. And h over here is the height. How high did we lift it up? But we need a little footnote here that says h is the height above some reference point. And you can set your reference point, your 0 point, your 0 height, to be anywhere that you want. Usually, you'll want it to be the ground. You'll want it to be as low as you can get. And then any height above that, you will end up imparting some gravitational energy into that object. Let's just take a quick sec to look at this formula. The gravitational energy equals mg times a vertical distance h. You'll see that that's actually the same thing that we have for work. The force that we did against gravity was m times g, and when we lift an object up, the distance is a delta y. It's a change in a vertical position. It's a height. So this equation is quite literally that equation, as long as the force that we're talking about is the force of gravity. Now, why this becomes useful is because when I lift an object up and give it gravitational energy, we can then transform that energy into other different kinds of energy. For example, if I was to drop it, just messing with you, we could turn that energy into a different kind of energy, a new kind of energy. Another form of energy that we're going to talk about is called kinetic energy. Kinetic energy is the energy associated with motion. So anytime that something is moving, we would say it has kinetic energy. When I'm running around the classroom, I have kinetic energy. And the equation for that says EK equals 1/2 mv squared. We're going to derive this equation today in our lab, where m is the mass of an object, and v is its speed. How fast is it moving? If the speed gets greater, the kinetic energy will become greater. And so we can think of examples where we do work to lift the mass up, it gains gravitational energy, and then you can later transform that energy into all kinds of different types of work. In this case, we're going to turn gravitational energy into kinetic. You will see that as this object descends, as its height goes down, its speed will go up. Here we go. 3, 2, 1. Right? We're used to watching objects in free fall, but now we're not talking about forces or motion necessarily. We're building on that by talking about this new idea of energy. What you just saw there was a transformation of energy from one type to another. And this pertains to an idea in physics called conservation of energy. We will say there's a law of conservation. This will always be true in any scenario in the entire universe. Energy conservation states that energy can never be created or destroyed, but it can transform into different types of energy. So the total amount of energy in the whole universe, in all of its different forms, is constant. It's conserved. And so this will hold true only for something that we call closed systems. And that basically means that you include everything, all the objects that you can think of, in a closed system. So for this case, there are actually two objects involved. There's the tennis ball, and there's Earth. Without the Earth there would be no gravitational energy. Without the Earth there, this thing would never gain kinetic energy on its way down. And as long as we include both of those in our system, we would say it's closed. There's no external forces coming in. There's nothing from the outside that's at play other than the tennis ball and the Earth. We're going to forget about me because all I care about is as it falls. And that would be considered a closed system, and we would have conserved energy in that case. The same equation will be true every time that you ever need to calculate any energy conservation. It will always say that the total amount of energy in the beginning is equal to the total amount of energy in the end. And if you are ever stumped on an energy conservation problem, this should always be the first thing that you write. And you can begin asking yourselves, what kinds of energy did I have in the beginning, and what kinds of energy did I have in the end? So far, you've only learned about two. We learned about gravitational energy in the beginning and kinetic energy in the initial state. And we also could think about those two energies in the final state. What kind of energy does it have at the beginning, and what kind of energy does it have at the end? So for the tennis ball, when I lift it up, it's not moving, but it is at some height. If it's not moving, this kinetic energy goes to zero. And then by the end, we're going to think about what happens to this tennis ball right before it hits the ground, right as it falls, and it's 1 millimeter off the ground at a zero height. It's basically on the ground, it's at zero. And that means that our gravitational energy in the end will also equal zero. So you'll always write out your total energy in the beginning is equal to the total energy in the end. You'll always write out your different types of energy that could be there, and then you'll decide which of those is zero, which of those goes away. And this will allow you to substitute in different equations for the different types of energy. In the beginning, I only had gravitational, so I would write mgh in the initial state must be equal to 1/2 mv squared in the final state. And if you knew something about the numbers, let's say I lifted the tennis ball up 2 meters, that's about as high as I can reach, and it has maybe 100 grams of mass, you could end up solving for how fast it would hit the ground. You could have done that with acceleration, but now we're going to start looking at it with energy, and you will find that it is definitely a shortcut in a lot of ways. You won't need to use kinematic equations anymore for this energy unit. You can just use energy equations. And that will make the math much easier for many of these scenarios. Okay. So that's energy conservation. And now the final thing that I want to talk about before we get into our lab is the new diagrammatic models for this unit. So for our diagrammatic models, there are two that we need to talk about. The first one is called a system state diagram. Effectively, it will tell you the state of the system at different times. So the system state diagram tells you what a system looks like at different times. That's the first one that we're going to do, and then that goes hand in hand with the second diagrammatic model that we have, which is called an energy bar chart. Energy bar charts tell you what kinds of energy are present at different times. So the system state diagram is basically a picture that tells you what the your objects look like at different points in time, and the energy bar chart will go right along with it to tell you what kinds of energy there are at these different times. So we're going to go ahead and draw a practice round. It's the same one that you saw on the PowerPoint. The way that you start with your system state diagram is you draw two panels, two images that you're going to fill in. So I'm going to, for my tennis ball example, I'm going to draw one rectangle right here, and I'll draw another rectangle right next to it. And this first rectangle represents the initial situation, and the second one represents the final situation. Now we draw our tennis ball. What did it look like in the beginning and the end? My tennis ball at first was up here. And it was raised some height. Sorry. It was raised some height h equals, let's say, 2 meters. I'm just going to put some random numbers in there for this example. And when it was at the initial state, it was not moving. So I would write v equals 0. That's enough for the initial situation. It's got all the relevant variables. You can see it with your eyes. In the end, my tennis ball is basically on the ground. It has a height of 0, and it's moving down with some velocity. And that velocity, we don't exactly know. So far, you and I don't know how fast it was moving. So we're just going to list it, but you could eventually solve for it. And that's a complete system state diagram. It shows the initial and final situation as a picture. Right below these system state diagrams, you draw our energy bar charts, which will start by drawing two sets of axes. And in these axes, we're going to put blocks to track how much energy changes around in the initial and final situation. So at the bottom here on the horizontal axis, let's create a little bin for the gravitational energy, and we'll create a bin for the kinetic energy. And the same we'll do in the final situation, a bin for the gravitational energy and a bin for the kinetic energy. This is effectively a histogram. And in these bins, we're going to start stacking up the different kinds of energy that we may have. This is a very simple example because it's all gravitational in the beginning, and then about right before it hits the ground, it's all kinetic energy. And so usually you'll be told how many total blocks to keep track of. I'm going to say we do 5 for now, but you'll start to get an intuition to know maybe I should only do 4 blocks or something like that, or maybe you'll need 10 if it's a more complicated situation. But for right now, I'm just going to stack up blocks where the energy is in the initial state. And I'm going to do 5 blocks, and I'm going to put them all in the gravitational bin. That's effectively saying that there's all gravitational energy and no kinetic. You can shade them in if you want. And then, when the ball drops to the ground, it will have all kinetic energy. Its height is 0, and it's got some speed. So as it falls, that gravitational energy goes down because I'm lowering my height, and I'm gaining more speed, and eventually all of the blocks go from the gravitational bin into the kinetic bin. And this is an energy bar chart for this situation. Often you can also draw in these little dashed lines to help you keep track of the different levels. And so much of the homework or Quizlets will have these dashed lines just so that you can kind of keep track of how many blocks go where. But what these dashed lines and blocks represent is not the exact number of joules that are there. It's not like there's 5 joules. What this represents is a relative energy level. This is saying 100% of the energy is in the gravitational bin. So each of these blocks is like 20, 40, 60, 80, 100% of all of the energy. And this is a really nice diagram because it obeys energy conservation. The total amount of energy that I had in the beginning, I don't know exactly how much it was, but that total amount of energy in the beginning equals the same total amount of energy that I had in the end. And so for this closed system, we obey energy conservation, and we have the same amount of energy in the beginning and the final states. Are there any questions about the content that was just covered? Anybody got any follow-ups or thoughts? Okay, then let's go ahead and get into our lab. Remember that you're going to take a survey, so let me know if this type of pre-lecture is helpful for you. I don't like lecturing for an hour, but 10 or 20 minutes doesn't seem so bad. So let's go ahead and start with our lab. Everybody will have a smart car in front of them. If you were on the computer last time, please rotate and let somebody else be on the computer now. Rotate, switch seats, wiggle your mouse and wake up your computer. Go ahead and turn on your smart car and get it connected to Capstone by using the sensor data menu. If you want to wait a sec, I can walk through that with you, or you can just go ahead and get it started. Nate, would you please kindly hand out some notebook entries for me? You? So I'm going to open up Capstone. I'm going to turn on my smart car. I see the Bluetooth button blinking. Remind me later, we go to sensor data, and you figure out which number is yours. Mine's number 42, and I'll go ahead and get connected by clicking it. No Tyler today? You know where Tyler is, Jason? Oh, you're there. Sorry about that, buddy. Yeah, my bad. No Jaylee today. All right. Once you're connected up, I want you to close this panel by clicking Hardware Setup. Get that out of the way. And our experiment today is called Puttin in Work. Now I want you to watch me do the lab for a sec, and then I want you to brainstorm about the different things that we might measure to start talking about energy and work. So I'm going to go ahead and put some mass on my car. This is actually the same experiment that we did last week, by the way. This is called an Atwood machine. Although last time we were talking about forces, this time we'll be looking at it through a lens of energy. So the main experiment that we'll be doing is we'll be looking at this car alone. I don't care about what's going on with the hanger. I want to look at this car and think about what kind of energy it has in the beginning, right now, and what kind of energy it will have in the end. So here we go. 3, 2, 1. Okay? We're going to watch a car accelerate to the right, and it will gain some kind of energy. And I want you as a group to brainstorm about the different kinds of energy that we might end up, or what kinds of measurables we might want to get data for. Which physical quantities do you think will be relevant for talking about the energy of this object? There are 5 that I can think of immediately, maybe 6, and I want you to brainstorm with your group, and then I'll come call on some people, and Jason will go first. But take 2 minutes or so to think about what are all the different variables that might matter. 1, 2, 3, 4, 5. If you get 5, you're in a good spot. Maybe a 6th that I can think of. But from that pre-lecture, there should be a lot of different variables that come up. So brainstorm. All right, let's see if we can get all 6 of these at least. So what are some things that you can measure about this car? Jason? Distance is definitely one of them. So we can measure the distance that it moves, and we would call, that's actually going to be the same as the position. That's what it'll read out to you on Capstone. I want distance, that's the answer I was hoping for. But if we start at a 0 position, whatever position it ends at, that'll be some distance. Mara?
The mass of the car.
The mass of the car is another good one. Mass of car. Great thinking. You got another one, Tyler?
Time.
Time. That is a good one as well. We could measure time, how long it takes for it to go across that track. Sam?
Can you do velocity?
Velocity is another good one. That'll definitely be a useful one.
Acceleration.
Alex, acceleration. Absolutely. Nice. Oh yeah, there's definitely maybe two more even. Lillian?
The mass and of the weight and hanger.
Okay, we can measure the mass of the hanger. Absolutely. Good, good. Planned for that, of course.
The height of the hanger.
Okay, we can measure the height of the hanger, that's right. Very good. I am mostly talking about the car, but these are good contributions. So I'm going to try not to focus too much on the hanger. So those will both be certainly important, but we're going to focus on the car today. Great suggestions. Got another one, Jason?
Gravity.
Gravity. Okay, it'll be 9.8, right? The gravitational constant, that's what you mean? Yep, okay. We'll list that as a constant in a sec. We won't measure that. It's a good suggestion, totally valid. Sam?
Speed.
Speed, we will also call the same as velocity in this case. This is good. Tyler?
Friction.
Friction, okay. That one I'm not going to put. It's a good idea. I see you guessing, right? We could measure it. When you say friction, what kind of quantity is that?
Oh, it would be a force.
It's a force. Ah. Okay, so we could measure the force of friction if we really had a complicated experiment. But maybe there's another one of those that isn't friction. Bobia? Force, yes, we can measure the force on this little hook right here, right? The force. And Bobia, what kind of force would you say is pulling this car along?
Gravitational.
Okay, yeah, that's right. Gravitational is pulling this, and it's transmitted through this thing, so what kind of force would be?
Applied force.
Or
tension force.
Tension force, yes, thank you. Very nice. Thank you for letting me go there. So the force of tension we could also measure, and we will talk about that. Last time we used a force sensor to measure the forces that were acting, but this smart car is very smart. It's got a little hook at the end there, and the harder that we pull on that hook, the more it will be able to measure the force that's pulling. Very nice. And so remember all the equations that we just talked about in our pre-lecture. We had, let's see, we had work, kinetic energy, gravitational energy. Those had things like mass, speed, height, gravity, like it was said. There's actually one other thing that I'm thinking of, and this one's kind of tricky. We sort of glossed over it. Lillian?
The angle.
That is the last one that I was thinking of. Yes. Technically, we could also measure the angle at which the force is being applied. And the distance, the angle between the force and the distance. So this thing moves a distance to the right, and it's being pulled on with a force to the right. So what would you say the angle is for this particular situation?
0.
It's 0. Force points that way, distance points that way. They're at a 0-degree angle from each other. But if I was to, let's say, if I was to pull this thing along, you know, at an angle like that, the distance still moves to the right, but the force is up and to the right. And so this might be maybe a 30-degree angle or a 40-degree angle. But you'll see that I would also do work by exerting that force over a distance. Okay. So the ones that we're going to worry about are, you'll know that I never actually said acceleration so far today. I mean, I guess I said it real quick when I said F equals ma, but there's no energy equation that actually uses acceleration. And since our angle is 0, we won't worry about measuring that. And since I said we're going to focus on the car, we won't worry about measuring anything about the hanger. And actually, in this case, you saw that for work and energy, time never showed up in any of those equations. This is one reason why energy is very useful, because it's actually not dependent on time. It just matters what something looks like in the beginning and the end. I don't care about what happened in the middle. I don't care about how long it took for the tennis ball to fall. All that mattered was its height and its speed. So we will actually veer away from talking about time as well. And we are left with 1, 2, 3, 4 measurable variables. Let's go ahead and put them in our notebook entry. Make sure that you know the standard units and the symbol. Go. And all their standard units. And before we select an independent and dependent variable, this one is actually going to be a little bit more complicated than our standard approach. Because we're going to ask, how does work depend on speed? But we didn't list work as any of our variables that we're going to measure. Can you even think of a way that we could figure out the work from some of these measured variables?
Since work is equal to force times distance, you just multiply the two.
Right, exactly. So we can extract the work by doing a force times the distance. So over here on the right side, we're going to have V as our independent variable. And we're going to have W as our dependent variable. Work is measured in joules, by the way. And this time, we're going to have to gather both the force and the distance and multiply them together to get these numbers. So right above here, I might write something that work equals F times D. Of course, there's a cosine theta in there, but the cosine of 0 equals 1. So we don't need to write that in. The angle will always just end up giving us a cosine of 0 equals 1. All right, now let's think about some experimental constants. Jason, can you think of something that'll be constant for this experiment? Gravity, the gravitational constant G, and I'm just going to write it as 9.80. We could either call it meters per second squared or newtons per kilogram. Let's go meters per second squared this time. Does not matter. And notice that I didn't put a negative in front of it because I did not put a vector arrow above it. This just means that the number, the size of gravity, is 9.8. We can ask what way it points later. There's going to be some other stuff that stays constant for this. Brainstorm with your group for a sec about which of these measurable variables will be constant and which of them will be changing. Go ahead and take a minute to discuss. Remember, this is what your experiment looks like. Go. So you ask yourself, which stuff stays the same throughout that whole experiment? Who's got a guess? There's one that's really obvious. Mara?
Mass of the car.
The mass of the car will certainly be a constant. We are not going to take any mass off of that. And let's go ahead and figure out how much your car has mass of. So grab your card, make sure you keep the little weights on it, and put it on the scale. Try not to let it roll. If it does roll, you can always put the car upside down and then put the masses to the side. Oh, geez, yours says overload. Huh. Anybody think of a way that we could maybe measure the mass of the car without overloading it? Tyler?
Take off the weights.
We can take off the weights and we can do them separately and then add them together. So let's do that. So you should have a mass of your car. Mine ended up being 754 grams or 0.754 kilograms. Let's make sure we write it in the standard units. But that is not the only thing that's constant. There's another one that's constant. Mohammed, do you think you know?
Distance.
The distance, okay. Would you say that the distance is constant if I was to stop this there versus there? Did it go the same distance when I stopped it here versus here?
No.
Okay, so a very good suggestion, and I can see why you're saying that. Every time we ran the experiment, it might go like 1 meter. But actually, we are going to end up picking different points for the distance. So that one, we're going to have changing. Totally a good answer, and I was hoping someone would say that. But we're actually going to say the distance is changing. Zoe?
Is the force changing?
Do you think it is?
Yes.
Yes, it is. That is correct. And we actually figured this out in our last class, that the amount of force that was pulling this thing along was dependent on how much I put on this hanger. I feel like my track might be curved a bit. There we go. And as long as this thing isn't bobbing around too much, the amount of tension in this string should be the same throughout the whole experiment, whether it's over here, or over here, or over here. So the force will be constant. Let's write Ft equals, and each of you has a certain amount of masses next to your hanger. You got a hanger and there's a little bit of mass. Every group has a different number, so make sure you put all of the masses that are at your table on, except for that big one. Don't put that big one. Put that on your hanger and go ahead and... How can we figure out the tension from the mass of the hanger? Tyler Pete?
Gravity times the mass.
But that's the formula for gravitational force. Do we have a formula for tension force?
Mass times acceleration.
You're on the right track. The gravitational force that's pulling on this string or on this hanger is transmitted through the string, and it just so happens that the tension force is equal to m times g, as you had noted. Just wanted to kind of pick on you a bit because we do not have a formula for the tension force. But if we were to draw a free body diagram, we would know that gravity's pulling down on that hanger and tension is pulling up on it, and those are equal. And so the tension throughout this is consistent, and I want every group to go ahead and calculate what your force of tension is for your situation. I've calculated mine because I had 100 grams on my hanger, but yours is probably different, I think. So you should have a different number there. We're going to make one other note as a precaution right now, so let's make a little footnote down there that says, do not let the car crash. These are new pieces of equipment. They're pretty expensive, so make sure that you catch it before it goes flying off the table.
Maybe it should come with a bumper.
It should come with a bumper. Yeah. Probably could have been more careful and set you up with some, but you know I'm lazy. All right, so we got our initial conditions and our precautions and the constants. Sketch of the experimental setup. I'm not going to do it for you this time. But just remember that everything that is shown up here as a physical quantity must be shown on the experimental setup sketch. So show where the distance shows up. Show where the speed is as an arrow. Show the mass of the car. Where does that show up? And show the force as an arrow. I'll let you do that in your free time. We're going to move on. For the graphical prediction, you will have work in joules and velocity in meters per second on the vertical and horizontal axes respectively. I'm going to go ahead and do my signature trend, and I want you to discuss with your group for about a minute or two what do you want to guess the prediction is, and do not forget to write an explanation of why you think work and velocity are related in such a way. Go! We'll talk about it when I'm not filming a YouTube video. Okay, everybody go to Capstone. And now we're going to have to gather some data from Capstone. We're going to have to gather the position, velocity, and force of this object. It's going. There we go, I'm back to being connected. And so what we will need is 3 plots. Go up to this little sticky note up here, this add plot axes, and hit it twice. 1, 2. We'll want position on the top. You will want force from the smart car in the middle one. So click the axis title and make sure that it has force on the y-axis. And then on the bottom one, we will want the velocity of your smart car. You'll see that I have x, f, and v. Effectively distance, force, and speed. And to do this experiment, all you will need is one good data run. It takes less than 5 seconds. So I'm going to go ahead and show you how to gather it. You'll want to hit record before you let go of it. Starting to record. I let go. And I stop it. Might have caught it a little early. And let's just zoom in a bit. I'll auto scale. I think I'm even going to scale it a little bit more. This is just for me. I'll show you how to do this later. 1 to maybe 4 seconds. Yeah, we'll even go 1 to 3. 1 to 3 seconds for my data, and we should be able to hit OK. And now you can see that in my position graph, I have a quadratic shape. It is curved up until I ended up catching it right around here. We have the force that was applied, which is constant as you had calculated, and we have a velocity that is increasing linearly in that range. What you will need to do is you will need to find 5 data points that you want to extract out the position, force, and velocity at 5 different times. So the way to do that, I'm sure that we'll end up talking about this again. The easiest way that I found is to use this little crosshair here. I'll click that, go to Add Multi-Coordinates tool, and it will give you a little tracker that you can use to drag around, right? Or you can just bump it up 1 point at a time. And so for me, it looks like I let go of my car right around 1.6 seconds, and it looks like I caught it again right around maybe 2.4. So it might make sense for me to take a data point every 0.2 seconds. So I'm going to go to like 1.8. And there I have my speed. I'll put that directly into my table. I will have my distance and my force. I'll multiply those together and put it in my table. And then I got the first data point, and I can drag this thing around to the next data point, maybe at 2 seconds, and I'll get some new numbers to fill in. And that is how you will get your 5 data points. So this is not going to be a very experimental day, but there's a lot of computer work and a lot of calculating. So maybe one of you will want to run the equipment, one of you will want to have a calculator in your hand, and one of you will be on the computer reading values off. Once you do that, you'll be ready to graph on the raw and linearized graph, and we'll continue on to the back page, where maybe you'll leave the diagrammatic models for us to talk about at the end, and you'll try the standard lab approach that we always have. Are there any questions before we get started?
You guys are gone.
Okay.
Alright, let's do it.
All right, let's get to it. So, we should have had work in joules on our vertical axis of our raw data. Good. And on our horizontal axis, we should have had velocity in meters per second. And if all goes according to plan, which, you know, science isn't always perfect. Sometimes science is a little more art than science. A lot of people don't get that. We should have had a quadratic relationship. That means that to linearize, you would need to plot work on the vertical axis and velocity squared on the horizontal axis. And I want to make sure that everybody puts v squared there. Don't just put a squared after the units. In fact, I want you to distribute your squared through so that it's meters squared per second squared on those units. Don't just leave it outside of the parentheses. And that should have given you a linear positive relationship. So, here for our graphical model, we have work in joules, velocity in velocity squared in meters squared per second squared. And do not forget to put that line. That line tells you that it is a positive linear relationship. My slope, I guess I'll go to this group. Sure. Because they had a nice shape, I think, if I recall correctly. Zoe, what was your slope?
0.4734.
0.4734. Good. And the units were joules over meters squared per second squared. Ugh. We have a fraction inside of a fraction. What you can do to get that fraction out of being in the denominator is called multiplying by the reciprocal of the denominator. Or, in other words, you would be left with 0.4734 joules times second squared per meter squared. That's one way that you can get that fraction out of the denominator. What was your b value?
0.0003.
Okay, nice. That is good.
One more zero.
Got it. Very small. And so I will put that in 0.0003. You probably predicted 0. Lucky guess. And your max value?
0.3234.
And your min value?
0.
Okay, nice. And I would anticipate that this got a very small percent.
0.0927.
0.09. Okay, 27, sure. Did anybody get above 5%? It's not wrong, just curious. Okay, one group that's...
Well, that was before we linearized.
Oh, okay, good. So, go ahead and do the calculation for the linear...
It was 4.6 after.
4.6, okay, good. Okay. Keep up the good work. Not a problem, not a problem. So in our specific math model, now let's start digging into this. We should have work as our dependent axis, equal to my slope, 0.4734. Sure, joules per meter square, and second squared ended up on top. My horizontal axis has v squared. And we're going to go ahead and write in our intercept, but that one ends up going to 0. So everybody, including this group, can go ahead and cross off their intercept. Hopefully we're all okay with this stage. We linearized by squaring v, so we got to make sure that we have v squared in that model. In the generic math model now, I can go w equals some slope, like k for now. We'll talk about what that is in a sec. Times v squared. And you know what? Let's not put in an intercept because it was effectively 0. So we're getting closer to the final model that we were trying to get to. And now the question is, what is k? What is our slope? Let's go ahead and think about this. Some groups have already figured it out, but some have not. Our slope currently has some number. I'm going to go 4734, and it's in joules times seconds squared per meter squared. And some of you might say, gosh, those are crazy units, but I guess it is what it is. But I mentioned that we can do some dimensional analysis in the lecture portion by recognizing that a joule is actually the same as a kilogram times a meter squared per second squared. So if I take that joule and put it in there, then let's see what we're left with. 0.4734. I'm going to put kilogram times meters squared per second squared. That's a joule right there. Times s squared over m squared. Lots of stuff right now. But you'll see some of this is going to cancel. For example, I have second squared on bottom right here and second squared outside on top right there. I have meters squared right here and meters squared on bottom, leaving me with just 0.4734 kg. The final units that this slope actually has units of kilograms. So what variable do we think belongs with the units of kilograms? M. Chelsea says M, and that's correct. So let's go ahead and substitute in M there. And which object were we actually tracking? The car. We're talking about the system as just being our car. So this should be the mass of your car, right? Let's go ahead and ask ourselves, let's write down the mass of our car right from the front page. My mass of my car, what was your mass of your car?
0.77.
0.77 kilograms. Is that number the same as that number? Not quite. And maybe there's a little bit of measurement error here, but what I'm seeing is a number that is basically 0.4 kilograms right here, maybe 0.5-ish, and I'm seeing one that is 0.8 kilograms right here. So how does the slope actually relate to the mass of my car? What factor did I have to multiply my car by to get that? 1/2. Correct, right. And soon I'm going to ask you how your slope matched up. 1/2. And now we should recognize this formula. We have 1/2 mv squared is equal to work. But work is the same thing as energy. Just sort of a transformation of energy. What happens was we did work to increase the kinetic energy of our car. So really what we just figured out is the formula for kinetic energy. And this is the final answer that I want you to have in a box somewhere in your generic math model. We just derived the equation for kinetic energy. Can I get a quick read from the room? What was the mass of your car and what was your slope? Okay, 0.9, yep. All right. So there is a reason why our numbers aren't matching up perfectly, and it's because there's actually more than just the tension force that's acting. What other force is actually acting, Tyler?
Friction.
Friction is also in here, and we never quantified that. We didn't do any work to figure out what the friction of the car was as it traveled on that track, and that's going to cause us to have a miscalculation for our work. And actually, the trend is that the heavier your car is, the more friction there is. So especially for this group over here that had 4 of these ridiculously heavy things, you're going to have results probably that end up being a little bit off. There actually also is something else about this classroom that I'm beginning to notice as I do this more carefully. These tables are not perfectly level, actually. You could put your little car on there, and you will watch it just start to roll. So the fact that we're not on a perfectly flat surface will also affect that. Okay, now let's keep going. The meaning of the slope. Did anybody try this one? May take a guess. Jason?
Well, so the number I have written down is incorrect because I haven't updated my numbers yet, but it should be as speed increases, work increases at a rate of blank joules over meters per second squared.
That's a fair way of saying it, yep. Zoe, did you say it a different way?
Kind of. I said for every 1 meter squared per second squared, the squared speed increases, the work increases by 0.4734 joules.
That is a very precise way of saying it as well. Both those are good ways of saying it. I'll stick with the for every way. So for every 1 meters squared per second squared, that's correct, that's a speed squared unit, the energy, or work, increases by whatever your slope value is. 0.47, yeah. 0.4734 joules is what mine was. But that feels weird. You would not ever say, for every 1 meter squared per second squared, the energy increases by that much. So we're going to add a little tagline onto this and say, the slope is 1/2 the mass of our car. That's really what it means in this case. And for the intercept, we should be able to recognize that as speed goes to 0, energy goes to 0. In other words, for an object that's not moving, there's no kinetic energy. And that makes sense given our equation that we had in the past. If it's not moving, if it's got 0 velocity, it's got 0 energy for the kinetic energy. I'll leave that available for you for a little bit. And now let's start talking about our diagrammatic models. We're going to draw a system state diagram and energy bar charts. And so for this one, since we're not dealing with a tennis ball that is moving in a vertical direction, we're talking about a car that's moving in a horizontal direction, I'm going to draw my little panels just like a really long horizontal rectangle, where the one on the left will be the initial and the one on the right will be the final. And now I will draw my car. From your perspective, it moved from left to right. So I'll start with my car on the left. And we're going to make sure we label all the variables. We say v equals 0. And I'm going to go ahead and set my reference point of this track to also be at a 0 height. I'm going to say this is 0, and the car just moved along that track, so it didn't actually gain or lose any height. In the end, my car moved over here to the right side. The height is still equal to 0, and it should have a velocity v. We need to draw that as an arrow. And our velocity equaled question mark. I don't know what it was. We could have got it from the capstone, but for now we just need to know that it does have velocity. Let's go ahead and zoom in a bit. There we go. Now let's try drawing our energy bar charts. Give me some axes. Let's say there's one. And here's another one. Okay. And for now, we just need to worry about our gravitational energy and our kinetic energy. Gravitational and kinetic, we'll add more next week, or maybe even in the practice session this week a little bit. In the beginning, I did not have any height, and I did not have any velocity. So I don't have any gravitational, and I don't have any kinetic. But in the end, I definitely have kinetic because I have speed. So let's go ahead and put a few blocks in there, just to show you that it doesn't necessarily have to be 5 blocks. I'm just going to put 4 this time. 4 blocks. But there should be something that's alarming to you about this that is violating something that we talked about already today. I'm going to go with Ari.
There's 4 blocks on the right, but there's one on the left which violates the conservation of energy.
That's right. So let's write out what Ari just said. Very nicely stated. This violates the conservation of energy. It looks as if energy was created out of nothing. There's some little footnote that I put at the bottom of energy conservation. Does anyone know why this situation violates energy conservation? Goodness gracious, look at you all go. Lillian.
It's an open system.
Exactly. It's an open system. What would we have had to do to our system if we were to make it a closed system? Lillian?
Include the hanger.
Right. We would have had to include the hanger. So let's make sure that we put a few notes in here and we say system equals car. We did not include the hanger, and the hanger had some kind of energy that it gave to the car. The hanger is the thing that did work on the car. But since we're not drawing that in our system state diagram and we're not including it, this is an open system. It's open to the environment. Stuff outside of it, an external force, is acting on our car. So we would write, this violates energy conservation because it is an open system. We'll gain more practice talking about open and closed systems in our next class, and definitely next week we'll do it a lot more. But for now, this is just our intro to realize that if energy is not conserved, that's because we didn't include everything in the universe that we could have included. But I will tell you right now that in the entire universe of this simulation that we live in, energy, the total amount of energy will be the same. So let's make a few notes. 1, system state diagrams. You draw the system in its initial and final states. So we draw a picture, and the other thing that we need to do is you label all relevant variables for energy. That's how you do your system state diagram. And for the energy bar charts, we draw axes and label bins of energy at the bottom. And then what we need to do is put blocks in each bin to represent the energy. Put blocks in each bin to represent the energy at different times.